Hello everyone and welcome back to the class. In today's class, first of all, we will discuss about the electric potential at the center of the charge ring. So here we want electric potential at the center of the charge ring, everyone. So let's see it. Here we have two cases. The case one, uniform charge distribution. So we are distributing charge on the ring uniformly, and in the second case, we are distributing charge non-uniformly, everyone. So here we have one ring, everyone. And total charge on this ring is, let's suppose, Q. And the radius of the ring is capital R, everyone. So we can see it here. In the first case, we are distributing charge on this ring uniformly, correct? And at this O point, we want electric potential. So here, what is the potential, everyone? In this case, it is KQ by R, correct? Now let's see next case, everyone. In the next case, we have non-uniform charge distribution. So again, we have ring, but now charge is distributed non-uniformly, everyone. So now we are distributing charge non-uniformly, and let's suppose total charge is again Q here. The radius is R, and at the O point we want, means at the center of the ring we want potential. So in this case also, potential is again KQ by R, everyone. So if we are distributing charge uniformly or non-uniformly, in both cases you will get KQ by R, everyone. So keep this thing in your mind. Now let's see it next case, everyone. Case number third. So here in the third case, what we are doing, everyone, we are taking one arc. Now we are taking one arc, everyone. And the arc angle is theta. And at the center of the arc, we want arc angle is what, everyone? It is theta. And at O point, we want electric potential. And total charge on this ring is Q, everyone. And the radius of this arc is capital R, correct? So total charge we are putting on this arc is Q, radius of this arc is capital R, and arc angle is theta here. So we want what is the potential at the O point. So in this case, again, everyone, potential at O point is KQ by R, correct? Again, we have same result, KQ by R. So if we have complete ring or we have part of the ring, in both cases, you will get KQ by R, everyone. So write down this thing. Now let's see it one question, everyone, on the basis of this concept. The electric potential at the center of two concentric half rings of radii R1 and R2 having same linear charge density lambda is. So here we have two half rings, charge density is lambda, everyone, radius is R1, R2. We want potential at the O point due to these both rings, correct? So let's see how we can do this question, everyone. This is ring number first and this is second ring. We know one thing, everyone. If we have full ring or we have half ring, in both cases, potential at the center is same, everyone. And if we are distributing charge uniformly or non-uniformly, then also potential is same, everyone. So this thing we knows already. So this concept we will use here in this question. So first of all, what I will do it, I will calculate charge present on the first ring, Q1. So what is the Q1, everyone? Charge density is lambda. And what is the length of this half ring? It is pi R1. Now charge on the second ring is Q2 and charge density is lambda and the length of the ring is pi R2. So if we will multiply pi R2 with the lambda, then we will get charge present on this ring, everyone, on the second ring. All right. Now the next thing is what, everyone? We want potential at the O point. So potential at the O point can be written as what? Potential due to the first ring and then due to the second ring. So we will write here due to the first ring K Q1 by R1, and due to second ring it is K Q2 by R2 everyone. Now the next thing is what we will put here Q1 value, and the Q1 value is what? It is lambda pi R1 divided by R1 plus K. Q2 is what everyone? Q2 is here lambda pi R2 divided by R2. Now what will happen here? R2 R2 will get cancelled out, R1 will get cancelled out. Then finally we have K lambda pi plus K lambda pi. So it is 2K lambda pi. Now we can do it one more thing everyone. Put here K value. So already we have 2 lambda pi, and K is what everyone? It is 1 upon 4 pi epsilon naught. So here pi is cancelling. So finally what we are getting? Here we have 2 and here we have 4. So finally we have lambda by 2 epsilon naught. This is the final answer everyone. And if you will check here, then we are getting option number B. So B is the correct answer for this question. Note down everyone. Let's see next topic everyone. Electric potential at the axis of charge ring. So here we have one charge ring everyone, and charge is distributed uniformly, let's suppose. And total charge is how much everyone? It is Q. Correct? The radius of the ring is capital R, and the distance between O and M point is small d everyone. So potential at M point we want, correct? Alright. So what we can do it here everyone? What we can do it here? First of all, we will write potential due to one small element. So I am considering one small element on this ring everyone. And charge on this small element is dq, correct? It is dq. So due to this small element, if I will write potential at M point, so it can be written as what everyone? dV equal to K dq, and now we want distance between this element and M point. So think it everyone, what should be the distance here? Sit, this is capital R, this is small d everyone. So use here Pythagoras theorem, so you will get distance. So R equal to what? It is under root R square plus D square. This is the value of small r, correct? Under root R square plus D square. So potential due to this small element at this M point is what? It is K dq by R everyone. Now the next thing is what? We want due to the full ring, so we need to integrate here. So now integrate on both sides. So total charge on this ring is what? It is capital Q everyone. So limit of integration is what? 0 to Q, correct? Now what about the R everyone? R is constant or it is variable? Think it everyone. So here R is what? It is the constant everyone. Why it is constant? Because if I will take this a small element, so distance between this element and this M point is what? It is a small r. For this element is also a small r. For this element is also a small r. For the all element everyone, the distance is a small r, small r, small r, small r. So here R is what? It is constant everyone. So keep this thing in your mind. R is constant here, correct? And according to rule, if R is constant, then we will put outside. So integration of dV is what? It is V. K and R both are constant, so put outside the integration. 0 to Q dq, and the integration of dq is what? It is Q everyone. And after putting the limit, we will get capital Q. So potential at M point we are getting K Q by R everyone. And what is the value of a small r? It is under root R square plus D square. So potential at M point we are getting K Q by under root R square plus D square. This is the potential at M point everyone. You can write down here Vm also. Finally, we got it potential at the M point. Note down everyone and keep this formula in your mind, correct? Note down. Let's see one question everyone on the basis of this concept. The two thin coaxial rings, each of radius a and having charges plus q and minus q respectively, are separated by a distance of s. The potential difference between the centers of two rings is. So here we want potential difference between a and b everyone. So let's see how we can do it this question everyone. So first of all, what I will do it here, I will write potential at a point. So this is first ring everyone and this is second ring. So potential at the center of first ring we will write first of all. So VA equal to what? It is KQ by A. And now we will write due to second ring at A point. So it is minus KQ by under root. Now so radius of this is what everyone? It is A and this distance is S. So distance between second ring and A point is how much? This is A everyone, this is S. So here if I will use Pythagoras theorem, so we will get under root A square plus S square, correct? So this is the distance between second ring and A point. Under root A square plus S square. Now we will write potential at the B point. So potential at the B point is what everyone? It is K, and on the second ring we have negative charge. So minus KQ by A, and due to the first ring at B point is what? It is plus KQ by under root A square plus S square. Correct? So this is the potential at B point and this is the potential at the A point. Now we want potential difference. See what is the potential difference here everyone. VA minus VB. So VA minus VB. KQ by A minus KQ by under root A square plus S square. Correct? Then minus minus is plus everyone. So KQ by A minus KQ by under root A square plus S square. So this thing we are getting. Now you can do it one thing, add this and this term everyone. First and third and second and fourth we can add here. So we are getting a potential difference VA minus VB equal to 2KQ A minus 2KQ by under root A square plus S square. Now 2KQ we will take common, so we have VA minus VB equal to 2KQ 1 by A minus 1 by under root A square plus S square. This thing we have. Correct? Now put here K value, which is 1 upon 4 pi epsilon naught. So we will get finally Q by 2 pi epsilon naught 1 by A minus under root 1 by A square plus S square. So which options we are getting here everyone? Option number 4. So fourth option is the correct answer for this question. Note down everyone. Let's see next topic everyone. Electric potential due to a thin uniformly charged rod at an axial point. So here we want electric potential on the axis of rod everyone. Correct? Length of rod is L here and distance between the point and the end of the rod is D here. And the charge density present on this rod is lambda coulomb per meter. And at this M point we want electric potential everyone. So let's see how we can find here. First of all, we will consider one small element on this rod. And the length of this element is dx everyone. Length of this element is dx. Correct? And the charge present on this element is dq. And the separation between this element and this M point is what everyone? It is x. Alright. So The potential due to this small element at M point can be written as what? dV equal to K dq by x. So potential due to this small element at M point is what? It is K dq by x. Correct. And we want potential due to this whole rod. So what we can do it here, we need to do it integration. So on both sides we are doing here integration, everyone. K dq by x. Now put limit of integration. First element is present here, last element is here. Correct. So limit of integration is what? D plus L. Correct. Now we need to put here value of dq also, everyone. And if you will look here the value of dq, so it is what, everyone? We know that lambda can be written as dq by dx. Right? So lambda can be written as dq by dx. Now the value of dq is what, everyone? It is lambda dx. So now put this dq value here. So we will get integration of dv is what? It is v, everyone. So v equal to d plus L. And dq value is what? It is lambda dx. So k lambda dx by x, everyone. All right. Now simplify this and see it what we will get. V equal to k lambda is constant, so put outside the integration. Inside the integration we have d and d plus L, everyone. And we have now 1 by x dx. So integration of 1 by x is what? It is log x, correct? So this is log x, everyone. And then put limit of integration d plus L. So we knows one property, we have log a minus log b, then it is log a by b. So we are putting here first of all upper limit minus lower limit, then we will get here v equal to k lambda log d plus L by d, everyone. And this is the final answer. So finally what we are getting, potential on the axis of this rod is what? It is v equal to k lambda log d plus L by d, everyone. Note down. Let's see the next topic, everyone. Electric potential on axis of electric dipole. So first of all draw electric dipole. This is minus q charge, everyone, and this is plus q charge. All right, and now this is the center of dipole. So ये length L होगी and this length is also L, everyone. We want potential at axis of dipole, everyone. So let's suppose we want at this M point. Name of this point is M, everyone. Okay. And the distance between the center of dipole and this M point is what, everyone? The distance we are considering R here. All right. Now the next thing is what, everyone? First of all, we want potential at the M point. So first of all, we will write due to this plus Q charge. So it is K Q by R minus L. And then we will write potential at the M point due to this minus Q charge. So it is minus KQ by R plus L. Correct, everyone? This thing we will get. Now the next thing is what here? KQ is common in both the terms, correct? It is same in both the terms. So take common here. Then in bracket we have R minus L minus R plus L, correct? So if you will take LCM, then what we will have, the next step everyone, R plus L minus R plus L divided by A square minus B square, A minus B, correct? A plus B. So this formula we are using here. So we have R square minus L square. Now this and this is cancelling everyone. So Vm equal to, we are getting KQ 2L divided by R square minus L square. Correct? This thing we are getting everyone. Now the next thing is what? This Q2L is what everyone? It is the dipole moment. So P equal to what? It is Q into 2L. 2L is the separation between the charges. So this is a dipole moment everyone. So Vm equal to, we are getting Kp by R square minus L square. This thing we are getting Kp by R square minus L square. This is the potential at M point everyone. Now here we are taking one case everyone. What is the case we have? If suppose we have short dipole, means we have very small dipole. So if we have a short dipole everyone, then what will happen? R is very large as compared to L, correct? So R is very large as compared to L. So L square is what? If, because L is very small, so definitely L square is approximately equal to 0. So what we are getting, Vm equal to, it is Kp by R square. So this formula is valid for the short dipole everyone. If the dipole is short, so this formula we will use Kp by R square, correct? So note down everyone this both formula. The second formula is valid for this short dipole. Now let's see next topic everyone, electric potential due to an electric dipole on the equatorial plane. So this is equatorial plane everyone, correct? And on this plane we want electric potential due to this electric dipole. So let's suppose here we have M point and we are finding electric potential at this M point. So distance between minus Q charge and M is what? It is X. And distance between M and plus Q is what? It is X everyone. So this distance is same due to this negative charge and due to this positive charge. Now at the M point we want, and this M point is present on this equatorial plane everyone. So due to this negative charge, potential at M point can be written as what? It is minus KQ by X. And due to this plus Q charge, potential at M point can be written as plus KQ by X. So potential at M point can be written as what? It is 0 everyone, correct? So potential at M point is what? It is 0. If I will take this point here everyone, then again potential at that point is 0. For every point, correct? For every point potential is 0 everyone, because distance is same here. That's why we are getting same potential. So on the equatorial plane we are getting 0 potential everyone. So note down this thing. Let's see next topic everyone, electric potential due to an electric dipole at a general position. So at general position we want electric potential everyone. So first of all draw one electric dipole. So this is minus q and this is plus q, and this is center of electric dipole, everyone, and at this p point we want. Correct? So this is the center of electric dipole, and this is the position vector, and this is the direction of dipole moment from negative to positive charge. And angle between, correct, P and position vector is what, everyone? It is theta. So at theta angle we want electric potential, everyone, and the name of this point is, let's suppose, x. Correct? So at this x point I want electric potential due to this electric dipole. So what we can do it here, everyone, we will resolve this p dipole in two component. So this is the first component, everyone. And this is second component. So if I will resolve this p along the r, then it is what? It is p cos theta. And this is p sin theta. Correct? So x point is present on the axis of this p cos theta dipole. Correct? See, if we have one dipole, everyone, and point is present on the axis of dipole, and let's suppose it is short dipole, everyone, then potential on the axis of electric dipole is kp by r square. This thing we know, correct? So when the electric dipole moment is p, then it is kp by r square. But in this case, what is happening? Dipole moment is not a p, it is p cos theta. So it is p cos theta. That's why on the axis it can be written as kp cos theta by r square. Correct? So at x point, potential is what, everyone? Due to this p cos theta, it is kp cos theta by r square. And due to this p sin theta, think it, everyone, this is p sin theta and this is the x point. Correct? And now this x point is present at equatorial position. That's why potential at this x point due to this p sin theta is what? It is 0. So it is 0, everyone. So net electric potential at this x point due to this p is what, everyone? It is kp cos theta by r square. And this is the final answer, everyone. Final result. So from this dipole, if I want electric potential at theta angle, so put here this theta value and you will get the electric potential at that point. If suppose this x point is present on the axis of electric dipole, then what is the theta value? Correct? Theta is what? It is 0, everyone. So if I will put here theta is 0, then cos 0 is what? It is 1. Then we are getting kp by r square. So when point is present on the axis of dipole, then theta is 0, cos 0 is 1, everyone, and we are getting kp by r square. And if suppose this point is present at equatorial position, then theta value is 90 degree, and when we have cos 90, then cos 90 is 0, then we are getting 0. Correct? So at any angle we want electric potential due to this dipole, then put here theta value and you will get the answer. So I hope this thing is clear, everyone, how we can write down electric potential at general position. Note down, everyone, then we will see it one numerical on the basis of this concept. Let's see it one question, everyone, on the basis of this concept. A short electric dipole has dipole moment of 16 into 10 raised to minus 9 km. The electric potential due to the dipole at a point at a distance of 0.6 meter from the center of dipole situated on a line making an angle of 60 degree with the dipole axis. So in this question, what we have, everyone, theta is given here. Theta is how much? It is 60 degree. P value is how much, everyone? P is 16 into 10 raised to minus 9 km. And we have R also, everyone. R equal to what? It is 0.6 meter. Correct? So R is 0.6 meter, P is 16 into 10 raised to minus 9 kilometer, and theta is 60 degree. So we know that, everyone, at general position, electric potential can be written as what, everyone? It is Kp cos theta by R square. Kp cos theta by R square at a general position. So all things we have, put in this formula, everyone, and calculate. So K value is 9 into 10 raised to 9. What is the value of P? It is 16 into 10 raised to minus 9. Cos theta, theta is here 60 degree, everyone, divided by R. So what is the value of R, everyone? It is 0.6. So 0.6 into 0.6. Now simplify this. So this and this is cancelling, everyone. Cos 60 is 1 by 2. So this is 8 here. And 9 into 8 is 72 divided by 36 into 10 raised to minus 2. Correct? This will go in the numerator, then it will become 100. So this is 2 into 100 is 200 volt. So finally what we are getting, everyone, it is 200 volt. Correct? So potential at 60 degree is how much, everyone? It is 200 volt. So correct answer is option third. Let's see next topic, everyone. Potential energy of a dipole placed in a uniform electric field. So potential energy we have required here, everyone. So this is direction of electric field, everyone. Correct? And in this electric field, we are putting one electric dipole. Let's suppose this is positive and this is negative, everyone. And initial angle is what? It is theta 1, everyone. So this angle is theta 1 and this angle is theta 2. Correct? So initial angle is theta 1, everyone, and final angle is theta 2 here. All right. Electrostatic force is acting in this direction. Due to this electrostatic force, this dipole is rotating, everyone. Correct? If I will write here torque due to this electrostatic force, so it can be written as minus PE sine theta. Why I am putting a negative sign, everyone? Here negative sign I am putting because due to this torque, the theta is decreasing here. Due to this torque, what is happening? Theta is decreasing. That's why we are putting here negative sign. If I will write work done by the electrostatic force, everyone, so it is what? It is tau d theta. Correct? Due to this small displacement, a small work we are getting, tau d theta. If you want a total work, so we need to integrate. So we are integrating, everyone. So tau d theta we are writing here, and we need to put here limit also. So initial angle is what? Theta 1, final angle is theta 2. So limit of integration is what? Theta 1 to theta 2. Put here tau value also. So the value of tau is what? It is minus P cos theta. Minus PE sin theta. This is the value of tau, everyone. Correct? Now what we can do it? PE is constant, everyone. So minus PE we will put outside the integration, and inside the integration we have sin theta only. And limit of integration is theta 1 to theta 2. This thing we are getting. So now the next thing is what? Fluid integration of sine theta. So integration of sine theta is what, everyone? It is minus cos theta. Now put limit of integration, minus sign we are putting outside. So work done by the electrostatic force we are getting here PE, upper limit minus lower limit. So it is cos theta 2 minus cos theta 1. So this is the work done due to this electrostatic force. We knows everyone, work done by the external agent equal to what? It is equal to minus of work done by the electrostatic force or conservative force. So in the same question, if I will write work done by the external agent, so it is PE multiply with the negative sign. So you will get PE cos theta 1 minus cos theta 2. This thing you will get. Correct? We know one more thing, everyone. Change in potential energy equal to what? It is equal to work done by the external agent. So work done by the external agent already we have. So what I can do it here, everyone, let's see it. Change in potential energy is what? It is final minus initial. Correct? And work done by the external agent is what? It is PE cos theta 1 minus cos theta 2. Correct? So this is the potential energy, everyone. UF minus UI equal to P cos theta 1 minus cos theta 2. So this thing we are getting. Now, if you want at theta angle, everyone, okay, and we are writing potential energy with respect to some reference, then what we can do it here, everyone. I'm considering theta equal to 90 degree as reference, everyone. So potential energy at 90 degrees is what? It is 0. Correct? So at 90 degree, we are considering potential energy is 0, everyone. So keep this thing in your mind. This is our reference point. Correct? So this is my reference. So 90 degree I am taking as a reference, and here I am considering at 90 degree potential energy is 0, everyone. So with respect to this, I am writing potential energy with respect to this reference. So this is theta 2, everyone. Theta 2 is 90 degree. So here potential energy we are considering 0. And this is U final also, everyone. Now U initial means potential energy at theta angle. We want, correct? So theta 1 I am considering theta, everyone. Theta 1 what I am considering? I am considering theta. So now what I will do it here, everyone. I am putting this condition in this equation. So what I will get? UF is what? UF means theta 2. And at theta 2, potential energy we are considering 0. So I will put here 0 because this is my reference. Okay. And UI is what, everyone? UI is U theta. Which theta 1 we are considering theta, everyone. And theta 2 we are considering 90 degree. And final position also. Correct? Minus equal to PE cos theta 1. Theta 1 is theta, everyone. And theta 2 is what? It is 90 degree. So cos 90. And the value of cos 90 is what, everyone? It is 0. So what we are getting? Minus U theta equal to PE cos theta. Correct? So now what we have? U theta equal to minus PE cos theta. If you will further simplify, then potential energy at theta angle is what? It is minus P dot E. If I will resolve this dot product, if I will remove this dot product, then we have cos theta. So at theta angle, what we are getting, everyone? Potential energy, it is minus P dot E. But keep this thing in your mind, everyone. Here, 90 degree we are considering as a reference point. Its potential energy at 90 degree, what we are considering, it is 0. So if I will consider potential energy at 90 degrees 0, then only this formula is valid. So this formula we have with respect to this reference point. Keep this thing in your mind, everyone. This formula is only valid if you are considering potential energy at 90 degrees 0 and you are considering 90 degree as a reference point. Then only this formula is correct. Alright? Note down, everyone. Let's see next topic, everyone. Stability of dipole. So here we have two cases. Case number 1, stable equilibrium. Correct? So in the stable equilibrium, what is happening? Let's suppose this is dipole, everyone, electric dipole. And this is positive and this is negative. So direction of dipole moment from negative to positive. And this is direction of electric field. So theta is what, everyone? It is 0 degree because theta is the angle between electric field and dipole moment. Both are in same direction. That's why theta is what? It is 0. So at theta angle, potential energy can be written as what? Formula we have minus PE cos theta. And theta is what? It is 0. Cos 0 is 1. So here we are getting minus PE. And this is minimum potential energy. And we know that if potential energy is minimum, then dipole is in equilibrium condition. Correct? So potential energy is minimum here, everyone. That's why it is a stable equilibrium. Correct? And if potential energy is maximum, then it is unstable equilibrium. Now let's see its second case, everyone. Case number 2, unstable equilibrium. So here what is happening? Now this is negative and this is positive. So direction of dipole moment negative to positive. And this is direction of electric field. So here theta value is what, everyone? It is 180 degree. So theta is what? It is 180 degree. So in this case, potential energy is what, everyone? Now we are putting here theta is 180 degree. So minus PE cos 180 degree, and cos 180 is what? It is minus, cos 180 degree is minus 1. So here we are getting plus P, and this is maximum potential energy. So when potential energy is maximum potential energy is maximum, everyone, then dipole is unstable, everyone. Correct? So note down this thing, everyone. Let's see one question, everyone, on the basis of this concept. What is the work done on a dipole to rotate it from stable equilibrium position to unstable equilibrium? So we want to rotate dipole from stable equilibrium position to unstable equilibrium position. Correct? So this thing already we know that if you are rotating any dipole, so work done by the external agent is what? It is PE cos theta 1 minus cos theta 2. Correct? This formula we know. So we will use this formula here, everyone. PE cos theta 1 minus cos theta 2. Correct? This is the formula, everyone. So if you are rotating any dipole in the uniform electric field, so work done by external agent is what? It is PE cos theta 1 minus cos theta 2. So here initially it is in stable equilibrium condition. So theta 1 value is what? It is 0 degree, and we are rotating to unstable equilibrium. So theta 2 is what, everyone? It is 180 degree. So for the unstable equilibrium, the angle between electric field and electric dipole moment is 180 degree. So theta 1 is 0 and theta 2 is 180 degree. Now put this condition here, everyone. So let's see what we will get. PE cos 0 minus cos 180. And the value of cos 180 is what? Is the minus 1. So minus is plus, cos 0 is 1. So we will get 2 PE. So work done by the external agent is what, everyone? It is 2 PE. This is the work done by external agent to rotate the dipole from stable equilibrium to unstable equilibrium position. So note down, everyone.